Today we're doing some more applications of using exponential functions. We're going to use the same formula as the PERT formula. If you'll recall, A is equal to PE to the R times T. P is the beginning amount. This was the ending amount. This is the rate of growth or decay or whatever it is, times the amount of time in the exponent. So we're going to use that exact same formula, except that the letters will be different, but that's not really important. What is important is what it all means. So in some of these, the A of T represents the size of the population of bacteria or people or whatever it is that we're talking about. A sub 0 is the initial amount. K is what we will call the constant, which is determined by the rate of growth. We'll be giving you enough information to calculate a constant. If K is greater than 0, positive in other words, the population grows or increases over time. This is the exponential law, or we call it the law of uninhibited growth. And so if K is less than 0, in other words, if it's negative, the population decreases or it decays is the word we're using over time. And the graph of these is pretty predictable. It looks like an exponential function. This is A at T, the initial amount. And this is the A-axis, this is time. And the graph just basically looks like an exponential function. Growth. As your eye moves from left to right, it's increasing. As your eye moves from left to right, in a decay, this is decay, when K is less than 0, the graph is decreasing. So here is your initial amount up here. And the graph would look like that's still approaching that asymptote. This is the t-axis, this is the amount axis. Okay, so some examples based on, and we're going to do a population, we'll do several different kinds. So based on data from the past 50 years, world population in billions can be approximated by this function where x equals 0 corresponds to 1950. So the first thing is, what is the rate of growth? Well, inside we know that this is the same as 1 plus 0.0185 raised to the x power. X corresponds to 1950. And so the rate of growth is 0.0185. And we estimate that world population will be, when t is equal to 50, for 50 years, plus 45. And that will equal 95 years. Okay. And so we would say that A at 95 is equal to 2.5, which is the given amount, beginning amount, times 1.0185 to the x power. And x, of course, corresponds to the years since 1950, which is 95 years in this case, for the year 2045. And this will equal 14.264 billion people. In what year will the population be doubled what it is now? And we're going to use the technique we used last class and just say, well, 2 is equal to 1.0185 raised to the x power, looking for x. And so the variable is in the exponent spot. So the only way to release it from jail is to take the ln of both sides, and we end up with the x times the ln of 1.0185. We're going to divide both sides by ln of 1.0185, and that's equal to x. So when we put that in the calculator, if you don't have a calculator, you would have to leave it at this point right here. You can't calculate any further. Typically, you'll have a calculator for this kind of a problem. So you have 37.813 years, but the question is, that's x. The question, however, is what year will the population be double what it is now? So this will happen during 1987. Okay. So now going to the next page. If the population of the U.S. continues to grow, as it has since 1980, then the approximate population in millions of the U.S. in year t, where t corresponds to z equals z, or corresponds to 1980, will be given by this function. So it's continuously growing. You estimate the population in 2015. So we have to first calculate t. T is equal to 20 plus, because there's 20 years since 1980 to get to the year 2000, and then 15 years past that. So t is actually 35 in this case. So the population after 35 years will equal 227 times e to the 0.0093 times raised to the also 35th power, which will be 314,332,083 people. When will the population reach half a billion? So half a billion in terms of millions is 500. So we'll use our same formula, but you do have to convert that to 500 million. E to the 0.0093t. And then solving for t, it's in the exponent spot, so we have to take the ln of both sides. We'll divide both sides by 227. And so we take ln of 500 divided by 227 will equal the ln of e to the 0.0093 t. And at this point, you realize that it's going to wipe. Ln of e is 1, and this brings the exponent. When we take the ln, we multiply by the exponent. Power raised to a power is multiplication, and the ln of e is 1, so it pretty much wipes it out. The ln of 500 divided by 227, and we're going to divide both sides by 0.0093 on a calculator, of course, and we will get t equals 84.909, and so, which is approximately 1980 plus approximately 84 years, because we're calculating the year it happens. So this would be approximate. It would be in year 2064, because even after 10 months of 1980, it's still going to be 2064. 11 and a half months would be 1264. So rounding an extra 9/10 of a year, it's still the same year. It doesn't change the year. All right, another application, healing, and they ask also what's the current population. So in year 2018, which is now, t equals 20 more plus 18, so 2018, And the population at this point now would be, whoops, this is 38. Population after 38 years will equal the same equation, 227e to the 0.0093 times 38. You can ask some interesting questions, but we're going to be using the same exact formula. And that gives us 323,225,433 people. Okay. And then we've got the next application where we're healing of the wounds. Another exponential application. In nature, we typically are using E. So the normal healing of wounds can be modeled by an exponential function if the beginning amount, A sub 0, represents the original area of the wound. And if A represents the area of the wound after n days, then this is the function that describes the area of the wound on the nth day, following an injury when no infection is present to make it go slower. Suppose that a wound initially had an area of 100 square millimeters. So if healing is taking place, how large should the area of the wound be after 3 days? So we're just going to use this exponential formula. The size of the wound, A, after 3 days would equal 100, which is the initial area, squared, 100 square millimeters, times E to the negative 0.35 times 10. Actually, times 3, because we're only doing it for 3 days. And that will equal, with a calculator, 34.994 square millimeters. It's the size. And then for part B, how large should it be after 10 days? So again, we do the same thing. A after 10 days is, again, 100 E to the negative 0.35 times 10. And that will be 3, and it's getting much smaller, 3.020 square millimeters. So under normal circumstances with no infection, it should be getting pretty small. Now, this is one that's typical, and that's pretty applicable to high school. Spreading of rumors. A model for the number of people in a community college who have heard a certain rumor is this, where P represents the total population of the community, and D is the number of days that have elapsed since the rumor began. In a community of 100 students, how many students will have heard the rumor after 3 days? So 100 is our P, or A sub P. And how many students will, 3 days is the T. 3. Or the D, is it's being used here. This is D, little d. And okay. So and there we go. So we've got, I think, what we need. So the total number N is equal to P times 1 minus E to the negative 0.15 D. And filling those in, we have 100 times 1 minus E to the negative 0.15 times 3 after 3 days. And when we use a calculator to calculate that, we get 36.237 students, but we don't want to chop students up to measure that, so we'll round that to 36 complete students. So if it's 36.8, we would still put approximately 36 students, because we're not assuming that any students are without legs or arms or fingers. We hope that we have students that are intact. I know that sometimes they're not, but hopefully we're doing the general case. Uninhibited growth for cell division. It's a universal process, they say, in the growth of many living organisms. We know that's true. Some of you are taking a lot of science based on an ideal situation in which no cells die and no byproducts are produced. The number of living cells present at a given time follows this law of uninhibited growth. So this is accurate for the early stages of growth. It certainly doesn't work for 100 years. So n sub 0 is the initial number of cells. And K is the rate of growth, commonly called the constant. It's the rate of growth. WTH, that's W, GROWTH of cells. Okay, so we've got bacterial growth. Okay, we're having trouble focusing. Some of you are probably having trouble focusing too. Staying awake is hard. So a culture of bacteria obeys the law of uninhibited growth. 300 bacteria are present initially. So that's n sub 0. And there are 500 after 1 hour. How many will be present in the same culture after 4 hours? How long is it until there are 10,000 bacteria? So n sub 0 is indeed 300. N1 after 1 hour of growth is 500. And we are looking for the n sub 4. So they have given us enough information to be able to calculate that K, so that we cannot solve this to answer the the questions, the last two questions, without knowing what K is. So we'll put this aside for a minute and we'll find K. When they give you a certain number that are initially, and then after a certain amount of time they give you another number, that is the information that you do need to find K. So we're going to use the formula to find K. So n at 1, so we have 500, is equal to 300 times e to the k times 1, which represents the hour. And divide both sides by 3, so we get 5 over 3 equals e to the k, and we could take the ln of both sides. And the ln of e, of course, is 1. And so there's our constant. And we're actually going to put that into the calculator, store it. Calculator. Sorry. Calculator. It's like I don't know how to spell calculator. C-A. Calculate. Okay, and so we're going to go ahead and put that in. Let me show you how to store it. You turn the calculator on. And then you just type in ln of 5/3. You don't have to count. Don't figure it out. And we're going to store that. So go down to this button here, stow, and we're going to store it as x. So that every time we type in x, we're going to get that number. So we can use that as our k. So at 4 hours is what we're looking for now. So at 4 hours, so n at 4 will equal 300, using the same formula, e to the 4 times, we could just write k, but since it's simple, I'll write times the ln of 5/3. But we have that in the calculator already as our x. And so that's what we're going to type in. We type in 300 times e, second ln, raised to the 4 times x power. Don't really need the times sign. And we get 2,314.815 bacteria. These you can leave as a decimal. I think we don't have much compassion for bacteria, perhaps. And then the second question, how long is it until there are 10,000 bacteria? So we are looking for T. So when 500, we want 10,000 in the end. So that will be the N. So 10,000 equals 300 e to the T we're looking for times the ln of 5/3, dividing both sides by 300. 100 over 3. T times K. That's the ln of 5/3. Okay, I'm going to take the ln of both sides. So we get the ln of 100 thirds over 3 equals T times K, because we take the ln of E to the TK, gives us just the exponent. So this will be the ln of 100 over 3 divided by K, which we have stored in the calculator, and that will equal T. So the ln of 100 divided by 3, and we're going to take all of that and divide that by x to get 6.864 hours. And then the final problem on this page, a population problem. The population of a Midwestern city follows exponential, of course. The population decreases, so it goes down from 800,000 to 600,000. I hope you recognize that we're getting some information here, a beginning amount, an ending amount, and we're getting a time frame from 1998 to 2000, so T equals 2. So what will the population be in year 2010? So we have to find K. And we're going to do that by using this information. 800,000 equals 600,000. E to the number of years, K times K, so KT, and it's times 2. We're going to just put 2 times 2. So we divide both sides, and we get 8/6. Oops. Okay, start over. Sorry. Find K. Our beginning amount is actually 800,000. It's not increasing, it's decreasing. Most populations increase. And times E to the 2K. And we divide both sides by 800,000 to get 6 over 8. And again, we're going to take the ln of both sides. No need to reduce this because we're going to put it in the calculators. Equals 2K, because when you take the ln of E, it's 1. And divide both sides by 2 to get K. And again, back to the calculator. ln, 6 divided by 8, so it's really 0.75, divided by 2, the whole thing. And that gives us a negative 0.14. Well, we're not going to write that down. We're going to store that as x so that we have our new constant. So this is K. So the ln of 6/8 over 2 equals K. That's what we're going to use in our formula to calculate what the population year will be in the year 2010. So in 2010, T will equal, since we're starting with 1998, it will equal 12. So we have the population after 12 years will equal the beginning amount times E to the 12 times K. And that's basically just a calculator activity. So 800,000 E to the 12x already stored in the calculator, and we will have 142,000 people. And we're going to round that to full people. So it's approximately 142,382 people. Full people. Okay. And now we're going to do some other types of problems. Radioactive decay, which is a common one in various fields. And again, we have an initial amount. The same formula. I hope you notice that it really is the same thing. K is less than 0 this time, so it's decaying. And so A is the initial, A sub 0 is the initial amount. And K is, again, the rate, this time of decay rather than growth. Okay, so they want radioactive iodine is a byproduct of some types of nuclear reactors, and its half-life is 60 days, which means that after 60 days, a given amount, so this is information they're giving us, will have decayed to half the original amount. So this is going to work a lot like our doubling does. Every time we have any initial amount, it's going to be half. The final answer will be half of that. So we're just going to use the number 1/2 in front. It will equal the final amount will be half of what we started with. Suppose a contained nuclear accident occurs. It gives off an initial amount C of radioactive iodine. So write an equation for the amount of radioactive iodine present at any time t following the incident, the accident. So we first have to find K. And so because of the half-life, any amount we have will end up being half of what we started with. So it becomes 1/2, and it will equal E to the formula they give us. 60 is the days, the time, times K. And we take the ln of both sides. And so K will equal the ln of 0.5 divided by 60. We'll store that in the calculator. So that we can call it back up. So the ln of 0.5 divided by 60. And we're going to store that as x. We don't even need to find the answer, really. We're just going to call it K. So the amount for any time t will equal C times E to the t times the ln of 0.5 over 60. So that's the answer for part A. And then for B, how long will it take for the radioactive iodine to decay to a level of 20% of the original amount? So again, it's not doubling. We're not taking half of it. We want 20% this time. So it's 0.2 will equal E to the ln of, that's our x, 0.5 divided by 60. The ln of 0.5 divided by 60 times, we take the ln of both sides. Sorry. Got times t. There we go. And we get the ln of 0.2, which will equal the exponent. So that's just the ln of 0.5 divided by 60 times t. So the ln of 0.2 over 60. is T. Okay, and so we will find that amount. So ln of 0.2 divided by the constant that we stored as x. And we get 139.316 days. How long it will take. Final application is Newton's law of decay, or law of cooling, sorry, which is temperature is decaying, I guess, and just it's a unique problem. We will give you this particular formula on quizzes or tests. It's kind of tricky to remember. Let me just talk about what it means and what all the notation represents when we see this formula. The U of T, that's the final amount. It's the temperature of the object that we're measuring at a given time T. Capital T is the temperature of the surrounding medium. It can be a refrigerator or an oven, room temperature maybe, but not typically. Maybe of an ice chest, that kind of thing. Ambient temperature, sometimes called. And then U sub 0 is the initial temperature of the object. So if you take something out of the oven, what temperature it is. K is the rate of cooling, how quickly it cools off, which we will measure by, in the same way we'll calculate K as we've done before, and T is the time. So we're thawing steak, thawing time of steak. Frozen steak has temperature of 28 degrees from the freezer. It's placed in a room with a constant temperature of 75 degrees. So after 10 minutes, here we go, the temperature of the steak has risen to 35. So we've got a beginning amount, an ending amount, and a time period. So we can calculate K, which is, in this case, so it's just our rate of cooling. After 10 minutes, we've got this. What will the temperature be after 30 minutes? So find K, first thing. We know that the temperature after 10 minutes is 35 degrees. So we can, that the room temperature is 75 degrees. And the initial temperature is 1028. And our time for this calculation is 10 minutes. So we're looking for K. So our ending temperature is 35 equals the room temperature, capital T, the ambient temperature where the steak is just sitting, plus the initial temperature minus that ambient temperature, times E to the 10 times K. Okay, so we're going to subtract 75. We get negative 40 equals 28 minus 75 E to the 10K. We're going to divide by that. We could actually calculate that, but we're not going to bother. So we'll get divide both sides by, and this cancels. And this ends up being E to the 10K. We'll take the ln of both sides. So we end up with the ln of negative 40 over negative 47. So this becomes positive, of course. Equals 10K. And we'll divide by 10 to get K. You don't need both those negatives. You can just put positive, and all of that's divided by 10. Okay, we're going to store that in the calculator. So we get the ln of 40 divided by 47. And then we're dividing that whole thing by 10. We're going to store that as x. Okay. And now we want to know after 30 minutes what the temperature will be. And so we're going to, U at 30 will equal the same equation, 75 plus 28 minus 75, times E to the 30. Okay. And we do the calculator. This is just a calculator activity, and you get 46.028 degrees. That's what the steak is. How long will it take the steak to thaw to a temperature of 45 degrees? So it certainly will take less time than 30 hours, but let's see. So it'll be, we want it for the final temperature to be 45, 75 plus 28 minus 75 times E to the KT. And we're just going to be a negative 30 divide by this 47 equals E to the KT, ln of both sides. So the ln of 30 over 47 equals the constant times the time, divide both sides by K. And so T will equal ln of 30 divided by 47 and divided by K, by the X that we stored. And we get 27.839 minutes is how long it would take, which is consistent. It is less than 30 minutes. Okay, so you have a test coming up. You have a quiz coming up on Thursday, Friday, this week of May 3rd, May 4th. We'll have a quiz. It will not cover this particular topic, but this is the last topic in the unit. So after the quiz next week, we will have a review day, and then we will take a test over this whole unit of logarithms and exponentials. Okay, go for it. Your homework.